The planet closest to Earth and second from the Sun is Venus. Sometimes Venus has been called Earth's twin, but the second planet is far from being our world's twin, as we will see in this program. I'm Larry Ross, Director of Space Programs at NASA's Lewis Research Center in Cleveland, Ohio. And I'm your host for this third program in a series of 13 called Journey Through the Solar System. Now let's go to a NASA film called Venus Pioneer.
Radar, which can penetrate the clouds, reveals Venus to be a nearly perfect sphere, close to Earth in size and density. While Earth tilts some 23 degrees, the axis of Venus is nearly vertical, and its orbit around the Sun is nearly circular, so it should have no seasons. It rotates backwards, or retrograde, so slowly that one Venusian day equals 243 Earth days. In fact, a Venusian day is longer than a Venusian year. Somehow its rotation is synchronized with Earth's, so that it always shows the same face to us whenever it swings closest. The major mysteries are in its atmosphere, a 70-mile thick blanket of nearly waterless carbon dioxide, so heavy that surface pressures are 90 times that of Earth. The surface temperature is an astounding 900 degrees Fahrenheit, twice as hot as an oven. Dark markings in the cloud tops move some 50 times as rapidly as the solid planet, and the clouds themselves appear to contain sulfuric acid. Earth-based radars reveal only crude hints of the surface beneath the clouds, vague outlines, but no clue on whether they are high or low regions. The first pictures from the surface of a boulder-strewn Venus were made by the Russian Venera spacecraft, an ongoing series of probes. Such was our knowledge of Venus in the year 1978, but that state of affairs would change radically because of the National Aeronautics and Space Administration's most comprehensive study of the atmosphere of another planet, Pioneer Venus. 2 coordinated missions, a task force of 6 spacecraft. One mission to orbit Venus for a full year or more, while the second sends 5 instrumented probes down through the clouds for simultaneous measurements over much of the planet. This is how it happened. An introductory question: how can the study of Venus shed light on our earthly problem?
One of the things we're looking for from this kind of study is the ability to do something that the laboratory scientist can do, to substitute for what he can do. He can experiment. He can try different conditions to see whether his theories are going to work out. If you're just dealing with the Earth, you're just dealing with one body like the Earth, you don't have this ability to experiment. In principle, you could start changing the Earth's atmosphere. I don't think that would be very much appreciated, and I don't think it's a very sensible way to test out our theories. So generally, we're stuck with the atmosphere as it is. Consequently, in planetary research can fill this gap to a certain extent, and we particularly look for examples and take specific interest in examples which to some extent fill this role by giving us phenomena which look very similar to a terrestrial phenomenon in some way, in some fundamental way, and yet are very clearly different. And then if our theories, which we've worked out for the Earth, can cope with that circumstance, we can be rather confident about them.
May 1978. The Pioneer Venus orbiter, first of the pair of missions, is at Kennedy Space Center for final preparations. It will carry a dozen instruments, a total of 100 pounds. Befitting a visit to a goddess, orbiter is robed in gold-plated blankets, the best-known reflector of unwanted heat. Its chariot, a reliable Atlas Centaur. great-grandson of America's first intercontinental missile and booster for the first Americans in orbit. It's still a mighty sight at liftoff. Setting off on a leisurely route to Venus, the orbiter chases its target more than halfway around the solar system, en route for more than half an Earth year. From its birthplace, the Hughes Aircraft Company's Space and Communications Group in El Segundo, California, the Hydra-headed multiprobe also goes to the Cape. Here, in last-minute preparations for launch, it meets the press. In all, 18 science experiments ride the 5 parts of the multiprobe. Today, this heat shield and the so-called sounder probe instrument ball it protected lie as scorched debris on Venus. Last chance for pictures. It also carries precious cargo to Venus, including this diamond, ground into an instrument window. Diamond is the only infrared transparent substance that can withstand the heat and pressure of the Venus atmosphere. Multiprobe's turn comes the night of August 8, 1978. The proverbial homesick angel, it sheds Earth's gravity to chase the orbiter more than 11 weeks ahead. On this cosmic merry-go-round, the multiprobe takes a different route through the gravity wells to arrive at Venus only 5 days behind orbiter. Near the planet, it will release the large sounder probe and 3 small probes. The drum-shaped bus itself comprises the 5th probe. It will burn up in the cloud tops. But first, the orbiter must be trapped into its proper orbit, the first moment of truth. Orders for this complex maneuver originate here at NASA's Ames Research Center near San Francisco. Within this building is the Pioneer Mission Operations Center, headquarters for this as well as all previous Pioneer space missions.
ACMO. Will you enter a base time of 23:45 and
Instructions go out routinely in the modern hieroglyphics that border on English, yet sound like gibberish to all but the controllers and their computers on the ground and in space.
1 Alpha Echo 0005.
1 Alpha Echo 0005.
CMO, ACMO.
CMO.
Loaded and verified.
Roger, thank you. Will you transfer it to the enable queue?
Roger.
Nearing Venus and some 40 million miles from Earth, the 2 spacecraft listen to and heed their radio commands. The pace is deliberate, yet precise to the microsecond. On November 16, the multiprobe turns to take aim at Venus, then releases the sounder probe. All of the entry probes will maintain radio silence for nearly 3 weeks to conserve battery power. Will they switch on again properly? There's no guarantee. 4 days later, the bus maneuvers again and loosens its grip on the 3 small probes. Orbit Day, December 4th, 1978. The controllers have done all they can. On the far side of Venus, an onboard computer must fire a retro rocket at precisely the right instant, in the right direction, for the right duration. It's known as a burn.
Telemetry from spacecraft continues to be normal, with no indications of any difficulties with command memory.
ESSI at 16.6.
Copy that. I see no data yet.
Timed for the convenience of Earthlings, the orbiter circles Venus once each 24 hours. Its low point deliberately dips into the very fringes of the atmosphere, while its long outer loop provides a vantage point for other instruments. Already, science data is flowing, and soon the first picture is returned by an American Venus orbiter spacecraft. A crescent with not much detail, but it holds promise of more and better images to come. As the orbiter watches overhead, the calendar closes in on December 9. The clock counts down to the single hour during which the 4 entry probes will taste the Venus atmosphere, feel the heat and pressure, and chart the weather on this neighbor planet. After the weeks of silence, all ears strain for the first whisper from the 4 probes.
We're waiting now for word.
Roger that.
Okay, we have it. We have the communications now. We can hear the transmitter from the sonar probe. We're right on time.
Watch probes on and locked up.
Drawn in by the Venus gravity, the sounder probe disappears into the sulfuric acid clouds. Dante's Inferno straight ahead. Past the main entry heating level, the probe sheds its heat shield and deploys its parachute. Instruments sniff the clouds, then relay their data straight home. Even as the computers spew their first inscrutable numbers, the scientists sense new mysteries and choose their words with caution.
Okay, that's mass 64. Don't say that's SO2. There's a peak in mass 64. Now, where's 128? 04.
Well, everything's working great. They're all coming down now. The parachute worked, and I guess we've got about 30 more minutes of just drifting down very slowly. It's going to take 30 minutes to go through that soup up there, and it is soup. I heard it's over 300 degrees already where we are, centigrade. The pressures are going up, but everything's working just like it was planned. I don't know how we can ask for anything greater.
After 17 minutes beneath the parachute, the sounder releases and free falls through the ever thicker and hotter atmosphere. Next question, will it survive the shock of landing and still send data? The probes weren't designed to, but it would be a nice bonus.
Impact, probe 4. Impact.
Yeah, they see the impact.
Roger that.
They've seen the impact. They were a few seconds early.
No, we lost it. Launch probe is gone. We have no more data coming in. Didn't survive.
Now, at 5-minute intervals, the 3 small probes impact Venus. 3 more chances for a survival. And it happened.
The daylight probe survived, it appears. There it is again. More. We're seeing the indication of good data coming in there. 39, perfect data. Right. We're about 52. Well, no, it's 20 minutes, and I'm predicting 20 minutes. Shut it off. It's phony data.
Now, the tension is reversed. Wagers on when the probe will die, either crushed and cooked or starved for power.
The interesting thing about this experiment being on the ground for an hour is that we had a chance to confirm the small amount of radiation. If we had 1 or 2 measurements, nobody would trust it. So we got gobs of it, so now we can go back and see if we can really trust it. It's beautiful.
Oblivious to the antics of the day probe, the bus now approaches its fiery rendezvous in the cloud tops. 2 instruments gather data for 1 critical minute.
14 looks like impact, bus.
And finally, 67 minutes and 37 seconds after the day probe landed on Venus,
We've just confirmed the loss of signal from the day probe.
You can imagine them sitting there seeing the temperature rise.
now the task of communications. Scientist to scientist, scientist to public. there are major mysteries. Certain sensors on all probes failed or faltered at the same place, about 12 kilometers above the surface. Another instrument detected a strange glow, either from the spacecraft or the planet. Were both mysteries due to static electricity, St. Elmo's fire, or a chemical reaction of some unforeseen sort? We may never know.
It's not condensable at any of the temperatures we see, and so there must be some rather potent chemical effect.
Within the wealth of chemistry data on the Venusian atmosphere, some surprises, but the promise of understanding to come later. There's apparently very little water vapor today, which leaves the question open, did Venus ever have oceans, and if so, where did they go? And there was one chemical finding that may shake the foundations of traditional thinking.
Perhaps the most outstanding result is the discovery that the atmosphere of Venus contains anywhere from 20 to 200 times as much neon, argon, and krypton as does the atmosphere of the Earth, whereas it contains just about the same amount of nitrogen and carbon dioxide. Now, we had expected, because these two planets have about the same size, about the same mass, that the amount of gas in their atmospheres would be the same. The fact that we haven't is going to force us to revise our theories of the origin of the planets and the origin of the solar system.
Many instruments on the orbiter and the probes work together to study the so-called particles and fields of near-Venus space. The solar wind, the ionosphere, the upper atmosphere. Because Venus has no strong magnetic field to fend off charged particles, the ionosphere seems to be constantly changing and fluctuating in response to variations in the solar wind. Another instrument on the orbiter makes frequent pictures of the cloud tops. Viewed in ultraviolet light, curious dark markings come and go as they rotate around the planet approximately once in 4 Earth days. This series of images, taken over a 2-week period, shows some of the recurring markings. Dark Y-shaped and bow-shaped features, and bright, high donut-shaped clouds surrounding the poles of Venus. Some of the most important new information comes from sensors on the probes as they sample conditions at points thousands of miles apart. They found changing, often violent winds at different levels in the clouds. They found that most of the incoming heat from the sun is absorbed within the densest clouds, although a small amount reaches the surface. And they found that below the clouds, the air is free of dust particles, and the temperatures and pressures are virtually the same all over Venus. And they found a complex sulfur cycle instead of a water cycle. The clouds of Venus are made of sulfuric acid and possibly hydrochloric acid, literally battery acid. It appears to rain out of the clouds and re-evaporate as it reaches the hotter regions below, a hail of fiery brimstone, literally. By coordinating data from all the probes, mapping of at least 3 major cloud decks around Venus is possible. One layer is described as being quite filthy, choking acid, smog-like conditions, filled with dust particles and debris. Sound familiar?
The interaction of solar radiation with smog and how it affects our weather, of course, is important on Earth, and Venus is an excellent laboratory for studying these kind of smog-like conditions and its effect on weather. We're not supposing at this stage that Earth is starting in the direction of Venus to become completely dominated by these smog-like materials, but certainly man's activity on Earth is pushing us in the direction of more and more pollution, and we'll be able to tell quite accurately, I think, in the long run, through the study of Venus data, Pioneer Venus data in particular, the effects of this increasing pollution on our future climate and weather.
On Earth, the problem of pollution has often been linked with the greenhouse effect, This trapping of incoming energy as heat was originally thought to explain completely the high temperatures on Venus.
The data that we have at the present time do not entirely support the greenhouse model. There seems to be more infrared radiation leaking out of the atmosphere than there is solar heating coming in. So that forces us to go back and re-examine the other candidate explanation that has been available for a few years, namely the compression heating of the gases as they are carried down from the cloud levels at the higher levels of the atmosphere of Venus down to the surface. Now, the experimental data that we've acquired seem to offer another possibility, that the solar heat is absorbed in the clouds where measurements show that it is indeed absorbed, and that it drives a vigorous circulation within the clouds. This circulation then causes the flow in the lower atmosphere to be dragged around frictionally by the principal driving cell which is in the clouds. The polar region of the planet has a difference that sets it apart from the lower latitudes, in that there appears to be a gathering of this circulation from the lower latitudes into a vortex. So we might say that there appears to be the equivalent of a hurricane sitting on the polar caps on Venus. The central portion of this is a region where the clouds are cleared because the infrared radiometer passing overhead in orbit is able to see higher temperatures by looking down through these holes in the polar cloud.
This is what that infrared radiometer sees. The important features are the twin bright spots or hot spots near the center. This is the first time any spacecraft has looked down on the North Pole of Venus. Apparently, we are seeing into deeper, therefore warmer layers of the atmosphere as the air over the poles rushes downward like water draining from a tub. This whole dumbbell-shaped hotspot rotates and wobbles around the Venus pole approximately every 3 days. A radar map around the orbiter charts elevation and types of terrain hidden beneath the clouds.
This is a map of Venus made by ground-based radars, and we're going to talk about 3 different areas that we've looked at with the Pioneer Venus spacecraft. This great northern feature, a region called Beta, and then an area near the Venus equator. The northern area was called the pear-shaped basin. When we got elevations from the Pioneer Venus spacecraft, it turned out to be a great plateau. Then there's a bright spot that's called Maxwell, and it turned out to be a high mountain range. So this great plateau is uplifted more than a mile above the Venus surface, and it has 3 great mountain ranges, one on the north, one on the west, and one on the east. This mountain range stands higher than Mount Everest does on the Earth. This great plateau is twice as big as the Tibetan Plateau, which is the biggest one on Earth, and it stands more than 3,000 feet higher. So this is a planetary scale feature. Just west of there is what we think a great fault zone that breaks the crust of Venus and extends for something like 4,000 miles. It has 2 great volcanoes along it. We think they're volcanoes. They have about the right slopes, and they stand more than a mile above the surrounding surface. We got a picture of the surface of Venus with the radar altimeter in the so-called imaging mode, and we've been able to compare that image with the ground-based images, and they match very closely. We'll keep going and get a strip like this all the way around the surface, whereas the ground-based radars can only see a short section. The most interesting thing about this picture are the round dark spots with little bright spots in the center. We've gotten altimeter traverses across them, and they look like depressions, and that means they may be impact craters, and we have impact craters on the Moon, Mars, Mercury, and the Earth, and it looks like we have them on Venus also. The importance of the preservation of the impact craters is that on all the other planetary bodies, the big impacts took place in the far distant past. That would say that this is very ancient Venus crust. The great plateau and volcanic mountains and fractures of the Venus crust and the gravity anomalies all say that the Venus is a very active, dynamic planet. Maybe a little less, maybe a little more than the Earth. It's a little too early to tell yet, but it does say that it's a very interesting place, and we're looking forward to continued observations.
To an artist, Venus looks like this: craters, mountains, and volcanoes, the source of the sulfur that colors and pollutes the clouds. Virtually continuous lightning from unknown origins, igneous rocks, basalts, and granites, probably involved in continental drifts that dwarf Earth's grandest features. Pressures like the bottom of an ocean, temperatures to melt tin, lead, zinc. Are there lakes of gleaming alloys? Are there clouds of metal vapor? Where did the water go? Where did the argon come from? As always, the rule remains: for every answered question, a dozen more arise. Our universe is a curious place. Men of science and of far vision will persist, must understand.
This is a photograph taken by the Soviet Venera 9 spacecraft in October of 1975. Another Venera lander made a chemical analysis of its landing site and found material resembling granite. The U.S. Pioneer Venus spacecraft, launched by the Lewis Atlas Centaur, orbited Venus. Radar was used to penetrate the thick clouds and give us images of the surface. The lower regions are blue. Yellows and reds show higher plateaus. Reaching as high as 11 miles above the blue parts is Ishtar Terra. It's about the area of the United States. Beta Regio has two extremely large volcanoes, together more extensive than the Hawaii Midway volcanic chain on Earth. We have much still to learn about Venus. Is Venus, for example, at a stage which will eventually approach Earth-like conditions? Or is it geologically dead and unchanging? This is Larry Ross saying goodbye from NASA's Lewis Research Center in Cleveland, Ohio. Next time, we will examine our home planet, Earth.